for this section, we've got some rules to learn about working with logarithms so that we can talk about properties of logs and we can do some multiplication, addition, and subtraction and division and things like that. So basically, I've put your product rule, your quotient rule, and your power rule up here at the top. And then I have a couple more little rules or actually guidelines that I'm going to show you about working with these logs. First thing we want to talk about is the product rule. Now it says if we have the log to a certain base and it's got two items in the parentheses beside it, which is the argument, that are multiplied, then we can say that's really the log of that same base of the first one plus the log of the same base of the second one. In other words, we can separate them out, and sometimes we'll want to do that as long as that base, of course, is not equal to the base 1. Now, the quotient rule says the sort of the opposite of that. If we have division, if the argument is being divided and it's the same base, well, we can just subtract the numerator first to the denominator next. And then the last one is the power rule. And it says if we have base b, log of base b, and it has an argument that is raised to a certain power, then we bring that exponent around to the front. We can take that exponent around to the front and multiply it times the log of that base times that argument. So those are things we're going to find are very convenient. There's an order to them. Really, the quotient rule is evaluated first, and then the product rule is second, and then the power rule is third. So if you want to do the order, I would put it out here and say this is the order they should be evaluated in. Now, I've got a couple more things I want you to say, also learn, okay? Let's write those in here. So also learn these rules. And the first one is this. If I have log of base b and it's raised to the b to the power of m, then I'm going to have, that is really going to be equal to that exponent m. Same base of the argument. Log base and the base of the exponential term are the same. So I've got the log base, the base of the argument are the same, then it is equal to that exponent. And let's just call that one the log rule, so we'll know what we're talking about. I've got another one that's going to help us a lot, and it's if I have a base and it's raised to a log, so it's raised to the log of base b and the argument is m, then it will also equal m, and that's what we call the exponent rule. And there's proofs for these that we will go over if we have time, or we'll basically see them as we're working the problems. But those are two others you should memorize. So on this page, you got 5 things that you really need to memorize so that you can work with these logs. Now, let's start and just basically start with some of the basics. We've got a log base 5, and the argument is multiplied. It's 2 terms that are multiplied. It's 7 times x. So we can separate that out. We can use the product rule to do it. We'll say this is really log base 5 of 7 plus log base 5 of x. And that means, of course, the two of them were multiplied together. Now let's look at the next one. This is really division, isn't it? 3 divided by 5. The argument is division. So we're going to use the quotient rule with this one. And we're going to say this is log base 3 of the numerator first. So that's going to be log base 3 of 3. And we're going to subtract log base 3 of 5. Now, if you can simplify them, once you've taken them out to this format, then you should. Now, log base 5 of 7, what it would really be saying is 5 to a power of y is equal to 7. And I can't seem to get those to simplify anyway, right? And I can't when there's an x involved either. But look at this one. We know what this one is. We know that if we have the same base as we have the argument, that this is equal to the number 1. Remember that? And so this is really equal to 1. Nothing we can do about 3 and 5 because we'd be saying 3 to the power of y is equal to 5. And since 5 is not a product, it's not a multiple of 3, then there's no way I can get that. It's not a product. It's not a, it can't be squared or cubed or anything. A power is what I'm trying to say of 3. So this is 1 minus log base 3 of 5. All right, let's do this next one, and they're going to get a little more complicated as we go on. So let's say this one is really the square root of 7. Now, what am I doing with the square root of 7? Well, I look at all radicals as fractions. So I'm going to say this is really log 7, base 7, of 7 raised to the power of 1/2. Now, when I have this 1/2, I can go ahead and do what I said over here. I can take it out front, right? I can multiply it. This is where it is. I can take it as an exponent. It can go out to the front and be multiplied times the log. So that's what I'm going to do. I'm going to say that is really 1/2 times log base 7 of 7. And that would be a further simplification of that one. And now, is there anything else that you see that can be done? And look, you should always see, if I have the same base as argument, I know that that is really going to simplify to the number 1, isn't it? So what have I got? I've got 1/2 times 1, which is really just 1/2. So that one we actually were able to get rid of everything except for the number 1/2, right? The fraction. All right, let's look at this one. Now this is log base 6, and these terms are multiplied together, so we're going to change it using the product rule. So we're going to change it to addition of the different logs. And you have to realize you've got 3 terms. You got 36, you got x, and you got y. So I'm going to say log base 6 of 36, and I'm going to add to that log base 6 of x, and I'll add again log base 6 of y. Can you put these in parentheses if you have a tendency to not remember which one is the base and which one is the argument of your log base, and which one's the argument? Go ahead and put them in parentheses, okay? Now, log base 6 of 6 is really saying something like this. 6 to the power of y is equal to 36. Well, can I write 36 as a power of 6? I could write it as 6 squared, couldn't I? And since 6 to the power of y is equal to 6 squared, I know that y, this whole term, is equal to 2. So I just simplified it doing what we learned in the last sections, right? So this is really 2. I can't do anything about that term that has the x. So I say log base 6 of x plus log base 6 of y. Okay, now let's take a look at this. One's going to look like it's going to be the quotient rule and the power rule used over here, because I've got division, but then I've got multiplication of these top 2 terms. So let's separate this out just one little step at a time. First, I'm going to say this is, and you can do it any way you wanted to, but I'm going to say this is log base 4, and I'll work with the numerator of 64, and I'll have to add to it log base 4 of x. Okay, I took care of the numerator. Now I've got to get the denominator. I'm going to have to subtract log base 4 of y. Now there's not much I can do with these x and y terms. They're pretty much set. But when I have numbers, I should always look and say, well, this is 4 to the power of y. Can I express 64 as a power of 4? Well, 4 times 4 times 4 gives me, and I would check it in your calculator if you're not sure of that, but say, you know, okay, 4 times 4 is 16. If I say times 4 again, I've got 64. So what is it? It's 4 to the power of 3, isn't it? That's what 64 is. Therefore, this value, log base 4 of 64, is really equal to 3. And then I say plus log base 4 of x minus log base 4 of y. Okay, next. For the next one, see if I can get this straight so you can see what I'm doing here. For the next one, I've got log base 2 of 8x raised to an exponent. It's raised to the power of 3. Now, because I've got this raised to the power of 3, I'm going to take care of that first, and I'm going to go ahead and move it to the front of my log 2. And then, but then I have to remember that I'm going to be separating out both of these parts, both of these components of the argument, and both of those were raised to the power of 3. So I'm going to have to think about it like this. I'm going to have to say this is equal to 3, and I'm going to put brackets here because I'll have to distribute it to these two things that I'm breaking out. I'm going to say 3 times log base 2 of the number 8 plus log base 2 of x. Now, I'm going to have to distribute that 3 for both of them because remember, they were both being raised to that exponent, weren't they? So, but at first, what is this? Well, it's that 2 to the power of y is equal to, can I express 8 as a product of 2's? Well, 2 times 2 times 2 is 8, so that's 3. Therefore, this whole term just became 3. So I've got 3 times 3 plus log base 2 of x. And when I finish that, what I'm going to have is 3 times 3 is 9. I'll come over here and finish it. That's going to be 9. And then I'll distribute the 3 again, plus 3 times log base 2 of x. And we've got a few more of these to work, and you might want to keep this set of rules handy when you're working this page. So kind of put a tab in page 19, if you will. This one, first one, we're going to look at what we're doing here. They're asking us this time to expand them. And I have log 5 of, and I have a quotient here, don't I? And so, but it's a complicated one, and then it's also raised to an exponent. So if I take care of this exponent first and bring it out front, it'll have to be multiplied times each of these components that I've got in here. So I'll really have to keep that in mind. But I'm going to bring my exponent out first. And I'm going to say this is 2, and here's my really big brackets that say I'm going to have to distribute it to all of this addition and division that I'm going to be doing in here, okay? So the first one I'm going to take care of is the log base 5 of x. And the next one I'm going to take care of, so I'll say plus, is, let me just put that in parentheses, is log base 5 of 5y. That's to another exponent, isn't it? And then what I got to do now is subtraction. So I'm going to be saying minus log base 5 of p to the power of 2. And then I'll say also minus log, well, I'll say plus actually. You know, it's really going to be hard to say what you're going to do here. You could say minus, and then you're going to have to subtract both of them, right? So here's another set of brackets, and this is addition here. Okay, so I'm going to subtract my denominator, which is addition, isn't it? Let's just do it that way. So maybe it'll be clearer that way. Log base 5 of, and the argument is q cubed. Okay, now everything should be taken care of, and I've got a separate set of brackets that I've got to use here. Now next, let's just go ahead and distribute this 2. It's got to be multiplied times 1, 2, and it's really going to have to be multiplied times terms 3 and 4, and I'm going to also distribute this negative while I'm doing it. So this will make this a negative term, and this will also be a negative term. So let's do that. So 2 times log base 5 of x is going to give me 2 log base 5 of x. And then I'll say 2 times log base 5 of this one, the second term, so that will be plus 2 times log base 5 of the term of y to the 5th. I'll take care of that exponent in a minute. And then I'm going to say 2 times, and this is going to be a negative, so it's going to be a negative 2 log base 5 of p squared. Take care of that exponent in a minute. And remember, I have to distribute this negative to both of these, didn't I? And I have to distribute this 2 as well, so it's going to be another negative 2 of log base 5, and this time it is q to the power of 3. I think I took care of 2, and I took care of distributing the negative both times I had to. So now I can just work on these individual terms. Now 2 log base 5 of x, there's nothing I can do about that one unless it matches up another term with another term, but I don't see anything. So I've got 2 log base 5 of x and 2 log base 5 of 5y of y to the 5th. Well, that 5 can come out in front, but it'll have to be multiplied times the 2, won't it? So now I've got 10 log base 5 of y. That's the only argument now. And look, I've got a 2 here that's going to have to come out front, an exponent, and it'll be multiplied times that negative 2. I'll have a negative 4 log base 5 of, and all I've got is p as the argument now. And this one has a cubed that's got to come out front, right? So I'm going to multiply that times that -2, so it'll be a -6 log base 5 of q. Now, if anything could be combined, I would do it, but I don't see any terms that are alike. I don't see anything else that can be done to these. Now, I do want to caution you, when you write log, as I've done here, it sometimes looks like I've written the number 21. That's why a lot of people don't write, they do it in cursive, okay? And say a log like this. So separate your numbers from your log or write it in cursive so that you can tell whatever it takes to make your math work. All right, so the next one, number 2, we've got some really interesting problems because this one's all being raised to the cube root. So what I'm going to do is separate them out first, and then I'm going to take care of that cube root by using fractional exponents, okay? So this is going to equal, first I'll say the numerator would be log base b of the cube root, and I'll just put that numerator in there all together so that I can separate later, okay? It's going to be x to the 5th y squared. And then I'm going to say subtract now log base b of the cube root, because remember, it's still under that radical, and it's 2 to the power of n. Okay, so I've taken care of getting rid of that. Now, the next thing I really need to do is go ahead and let's go ahead and split these out. So this is going to turn into addition, and this is going to turn into, well, this won't turn into anything. So let's just split this first one out, okay? I've got log base b, and I'll say this is the cube root of x to the 5th, and I can do that because these terms are multiplied. So it's really plus log base b, and it's still the cube root, isn't it, of y squared. Okay, so I split those two out. Remember, I could have written this again. This is the cube root of x to the 5th times the cube root of y squared. So that's why I'm able to split them out with my product rule and change it to addition. I'm really not doing anything with this third term, so I'm just going to write it down again. Log base b, and it's the cube root of 2 to the power of n. All right, now let's think about these radicals as fractional exponents. Now I've got 3 is the root, and 5 is the exponent. If I write that as a fraction, and you're going to have to remember this from taking 1033, then I write it as x to the power of, now the root goes underneath, and the exponent goes on top of the fraction. So I've got log base b to the times of x to the power of 5 over 3. That's my argument, okay? Let's look at the next one. This is log base b. And if I write this one as an exponent, then remember to put the root underneath and the exponential part on top, okay? So it's really y to the 2/3. And the third one, I'm going to say this is really log base b. And I'll say it is, now this one is already, I'm going to just say it's going to be of the 2 to the power of n over 3. There you go. All right, now what can we do? Well, we've got exponents, and we can take these exponents out in front of our logs, and that's what we're going to do next. So this one is going to be 5/3 times the log of base b of x, okay? This one is going to be 2/3 log base b of y. And this one that I'm subtracting is going to be n/3 of log base b of 2. That is the simplest format. That is the most expanded version that I can come up with. If I could simplify any of these, I would, but nothing here is going to it's going to simplify it all for me. All right, now let's talk about log of 1000x times the square root of x cubed minus 1. Now I can't split this out. I just want to make note of that really early. I can't split this out into using the product rule x cubed and 1 because it's not multiplication under this radical, it's subtraction. So I'm sort of stuck with it the way it is. And the other thing you need to note is that when it says log without a base, the base is 10, okay? So this is the common log, base 10. So let's go ahead and divide this out. We'll say this is log of 1,000. And then it's plus because it's times the log of x. And then it's plus again because it is times again log. And this is where we say this is the radical. Square root of x cubed minus 1. Now, log of 1,000, log base 10 of 1,000 is really saying 10 to the power of what is going to, can I express that 1,000 as in powers of 10? Well, it would be 10 and there's 3 zeros, so it's 10 cubed. So this term right here simplifies to the number 3. Remember, log base 10, so I said 10 to the y is equal, looking for that unknown exponent, and then I said set it equal to something with a base of 10. That was a power of 10. All right, now there's nothing I can do with log of x until they tell me what x is. And this one I can fix a little bit. I'm going to go ahead and write this with a fractional exponent. So what would it be? Well, it would be to the power of 1/2, wouldn't it? All right, now once I have a fractional exponent, I'm not finished, am I? So this is still 3. This is still plus log of x. And this is 1/2 times this log of x cubed minus 1, which there's nothing I can do until they tell me what x is. Okay, next one. Now this one is ln, so it's the natural log. So really what this is, ln, remember, is log of e, isn't it? That's the base e that we're looking at. So let's think about it that way because it might help us in simplification. And for right now, I'm just going to write it as ln. And I do have a tendency to write these in cursive because they can get kind of confusing. You're just going to have to figure out what works for you. So this is going to be, I'm going to start with the numerator here, and I'm going to say this is ln. And the argument of it is the square root of e times x. So that's 2, and I'm thinking, okay, I'm going to split those out with the power rule later. I'm going to subtract that denominator, but look, there's multiplication, right? So I can say, okay, subtract, and I'll put it in parentheses because I've got to subtract both of them, don't I? And so this is going to be ln of x plus ln of x plus 10 cubed. Now you could have done that in stages. You could have subtracted ln of x times x plus 10 cubed and then split it out into addition later, but whatever works for you is fine. Now I'm going to say, do I know what to do here? Well, I know I'm going to split this out again, right? I'm going to go ahead and do that. So this is ln of the square root of e, and that's going to be plus ln of the square root of x. I took care of that first one. And now as I divide this out, I'm going to say minus. This is minus ln of x, and also distribute the negative, right, to both of these. And it's also going to be minus ln of x plus 10, and that's cubed. All right, so what can I do now? Well, these radicals are really exponents, and they're square roots, so their exponent is 1/2. And just let's go slow with this because this is new stuff. This is e to the power of 1/2, isn't it? And this is x to the power of 1/2. And this is nothing because this is just ln of x, isn't it? And this one is going to be minus ln. And this one, I'm going to go ahead. I should have gone ahead there and said, let's take the 3 out front, right? And say it's ln now of x plus 10. 3 ln of x plus 10. So I took care of that one. Now look at them one at a time and see what we can do. This term has an exponent. Well, let's take the exponent in front. So this is really 1/2 times the natural log of e. And this one is 1/2 times the natural log of x. And this one is just a negative the natural log of x, isn't it? And then this one is minus or negative 3 times the natural log of x plus 10. So once we've done all of this, I begin to see that I have some things that are the same. And I want to be able to simplify by adding like terms. So I look at my terms one at a time, and I recognize right away that this one has something that I can fix. The natural log of e. Well, remember, this is really log base e of e. We have the same base and we have the same argument. That is the number 1, always. So what have I got here? I've got 1/2 times 1. Okay, I took care of that one. It's just going to be equal to 1/2. What about this one? 1/2 the natural log of x. Well, there's nothing I can do. But wait a second. I also have the natural log of x here. This is minus 1 times the natural log of x. So these are like terms. So I have a positive 1/2 natural log of x. I have a negative 1 natural log of x. When I combine them, I end up with a negative 1/2 times the natural log of x. Parentheses if you like. And then nothing really to do over here. So I'm going to just say it's a minus 3 times the natural log of x plus 10. And of course, this would just be 1/2, right? I can just, rather than rewrite it again, let me just say there. It's 1/2 minus 1/2 times the natural log of x minus 3 times the natural log of x plus 10 is my answer. Now on this page, I've repeated the properties for condensing logarithms here, the product rule, the quotient rule, and the power rule. And if you're looking for the order of them, once again, you just keep in mind that the order of those is going to be quotient rule first, and then the product rule, and then the power rule, okay? Is the way you kind of work those. Now, I want to take these and actually condense them, and where possible, evaluate them without using the calculator. So that's kind of what we've been doing, and this is just a couple more. So when I look at it, and these have already been stretched out, haven't they? They've already been decompressed, if you will. And what I'm going to say for this one is this is really going to be, since that is going to be the product rule, right? I started out with them being added, so I will end up with multiplying the arguments together. And so this is going to be the log of 100. Now wait a second, because I recognize that log base 10, and if you are having trouble thinking about that common log yet, it's log base 10 of 100. Well, 100 is a power of 10, right? So if I was looking at it right over here, I'd say 10 to the power of what would equal, and I write 100 as a power of 10, it's 10 squared. So that y is equal to 2, isn't it? So this whole thing is equal to 2, and I simplified it just by bringing it together with the power rule. It really simplified it for me. Now let's look at this one. This looks like, because, and I've changed this. If yours says 3/5, please change it to 3/2, because we're going to use 3/2 instead of 3/5. And then what this one is going to say, let me just make a note of that. Okay, so I changed that fraction. Now what this one is going to say is I really need to kind of look at this as subtraction first, which is, but then I'm going to raise it, this first one, to raise it to an exponent, right? And the exponent is 3/2. Okay, let's do that first. This is the natural log of 9 raised to the power of 3/2. Okay, does that help? All right, that's the first term. And then I'm going to say subtract the natural log of 54. Haven't got anything I can do with that one, except this subtraction brings to mind the quotient rule, doesn't it? So when I have that, and I'm wanting to condense them, I'm going to say, well, this is really the natural log, and I can do all this only because they have the same base. And this is, in the numerator, I'm going to say 9 to the power of 3/2. And in the denominator, I'm going to say 54. Well, 9 to the power of 3/2 is an interesting term. And I'm just going to kind of look at it like this. It's really the square root of 9 cubed, okay? The square root of 9 cubed. Now, when you have this, and over 54, of course, but when you have this written like this, you can also write it, this exponent can be either inside or outside that radical, and it works the same way. So for this one, it might be easier to think about as the square root of 9, and then I'm going to cube it, because the square root of 9 is 3, and 3 cubed is really 27, right? So just keep that in mind. That exponent, when you're doing this with radicals, that exponent can go either inside or outside of the radical. Now, what that brings me to is I've got the natural log of 27 over 54. And 27 and 54, 54 is 2 times 27. So I can reduce this. I'm going to come out here and say, okay, well, this one is really the natural log of 1/2. All right. Now, what do I do about that? Well, it's a fraction. Let's look at it with an exponent and see what happens, because it might simplify even further. So I would say this is really 2 to the power of -1, isn't it? And if I brought this out front, wouldn't I say this is negative the natural log of 2? Now, lots of different ways that you could write it. All of this is the same thing. Natural log of 1/2 is the same as the natural log of 2 to the -1, which is the same as negative the natural log of 2. We're going to keep on going. We're really doing the same thing here. We're going to try and compress these or condense them down. And this one has really it has a leading coefficient in front of that natural log term, so I know I'm going to have that one as an exponent, right? This one does too, but it's also subtraction, so I'm going to kind of separate it out like this. I'm going to say this is the natural log of x raised to the power of -3. That takes care of this part. And then for subtraction, I'm going to divide it. Well, why don't we write it down first? What is it? Well, if I bring this exponent out, I'm taking care of the negative with my subtraction, okay? So I don't have a negative exponent. I've got y to the power of 5. Okay? So now what do? Well, now I say natural log of x to the power of -3, and I say divided by, well, let's do it like this. Divided by, just needs to, the argument needs to be divided by y to the power of 5, okay? Okay, so now what's the next step on this one? Well, this -3 is really a fractional exponent, right? I mean, it's really, you can think about that as a fractional exponent. I would move this down and say this is really, if I wrote it out for you, it would be the natural log of x cubed, right? Okay, 1 over x cubed, and that's the numerator part of it. And the denominator over here is y to the power of 5, isn't it? So what I've really got is I've got to kind of bring these exponents to, bring these terms together. So I've really written it kind of wrong here, because this x cubed should have gone down in this denominator with the y to the 5th. So why don't I kind of do that part over again and say I've got the natural log, y to the 5th is down here in the denominator. X cubed, I'm going to bring down here in the denominator. And what do I got left in the numerator is just 1, okay? Taking care of it a much better way. All right, now, what can I say with this? Well, this is interesting, because anytime you have a 1, you have the natural log, the log of 1, any log of 1. Log base 10 of 1, the natural log of 1, log base 7 of 1 is always equal to 0, right? We know that. So what I could say is I can take this kind of back out now and make it even simpler than it is right now. I can say this is the natural log of 1, and it's going to be minus the natural log of x cubed y to the power of 5. So I compressed it, and then I'm going to have to kind of stretch it back out so that I can resolve this natural log of 1, which is always going to be 0. The natural, any log of 1 is going to be 0, okay? And then what do I have here? Well, I have, this is the natural log of x cubed y to the 5th. And if they wanted me to stretch that out into, but they didn't. This was compression that we were working on, wasn't it? What have I got? Negative the natural log of x cubed y to the power 5. Okay, hopefully that one wasn't too confusing. Okay, let's take a look at problem number 4. And these can be really confusing. I'll try and see if I can be a little clearer with this one. First of all, I'm going to take this fraction, this this leading coefficient that's a fraction, and I'm going to pull it over as an exponent. And I'm going to do that to each of these terms. Take the leading coefficients and turn them into exponents so that I can kind of start compressing these. So this is going to be log base 2 of x to the power of 1/3. And I'm going to add to that log base 2 of y to the power of 2/3. And then I'm going to subtract log base 2 of z squared. Okay, so all I did was take these leading coefficients and turn them into the exponents at the ends. Now, let's see what else I can do with this. Everything is log base 2, so I'm going to say this is all log base 2 of something. And these two are added, that one's subtracted. These two are going to be multiplied and inside the numerator. And this one will be subtracted, so it will be the denominator. So I'm going to change this into a big fraction. And I'm going to say this is going to be, and this is my argument, so I'll go ahead and put it in brackets. This is going to be x to the power of 1/3 times y to the power of 2/3. And it's going to be divided by z squared. Okay, that's very simple. Now, what else can we do here? Well, we can look at these as radicals, can't we? Because this is really going to be the cube root of x, and this is really the cube root of y squared. So let's see if that helps us any. A lot of times we try something and it doesn't necessarily simplify, or it doesn't help us to compress it. So let's just see what this does. I'm still going to have in the denominator z squared, but I'm going to change this into the cube root of x times the cube root of y, and this time I'm going to leave the exponent under here, y squared. Now I recognize the fact that I've got two cube roots multiplied together, so I can just put them under one radical sign, can't I? So this is going to be log base 2, and I'll keep my brackets going like this because it's kind of big and it's a fraction. And this is going to be the cube root of x times y squared, and the denominator is still z squared. And I don't think there's anything else I can do for this one, so that one's probably finished. Now on page 23, we're going to go back over what we've been over just briefly at the beginning of this, which is the change of base. Now I showed you the change of base before, the property that you can use, because if you're using an older calculator like a TI-84, then you really don't have the option of putting in a different base. You're either going to have to use the natural log or the common log, and so you would have to represent everything as a fraction, right? So to change the base, what we did before was we said, you know, we used the calculator, we just said log base 10, for example, and we put the argument in the numerator, and then we put log the same base 10, of the old base, and once we did that, it converted it to the new base 10 is what it's doing. So we can use this change of base function, and we should, and I've got some instructions here that need changing. It says use a graphing calculator. At mine, I've changed them already. Use a graphing calculator. It used to say a graphing utility. So use a graphing calculator, change the change of base property to, and not graph, we're going to just evaluate each function. So if you'll make those changes to your handouts if you have them printed wrong. Now what this means is I want to show you what happens. So I've changed it. I've written from log base 2 of 5, I said to convert it to the natural log, I would say, well, natural log of 5 divided by the natural log of 2. Natural log of 5 divided by the natural log of 2. Over here, I've just said, well, what's the conversion going to look like if I use changing it to base 10? What's it going to be? Now I've changed it here to base E, and now I've changed it here to the common log base 10. And let's take a look at it with calculators. Now there's a kind of interesting feature on your calculator if you have the TI-84, then you have the ability to just hit the math button and then hit the alpha button, which is the green one, and then hit the math button again, and it brings the log feature up for you. So what I could say here is log base 2 and come over here and say 5 and then evaluate it, okay? And it would tell me what it was. It's 2.3219. I found that just by plugging it in. But what if I'm wanting to look at it with a calculator that doesn't have that feature? I can look at it as, I can change it to the natural log base. I can say natural log of 5. And I can divide it by the old log base, which is, and I'm having to use the natural log because it's the new one, right? And so I say natural log of 2. And when I do that, I've got the same answer. You see it? What if I use the log base 10, which is this, the common log, to do the conversion? Well, I would say log of 5. And I'm going to say divided by, and I'm going to use log of 2. And I get the exact same thing. So no matter what I do, whether I use the TI-84 feature or whether I do the conversion, getting to the new base, base E and base 10, I get the same number when I evaluate. So all of these come out to be, 2.3219. We'll just round it to 4 decimal places. Now, I wanted a little more practice with changing these. So add a page here, and we're going to call this, we're going to say add to guided notes. And I said 5.3, page 23. So add these to that page 23. And the first one I'm going to do is going to be to convert. And I'll say this is log base 7. And I'm going to convert it is of negative 2z. And I'm going to convert it to base E, okay? I'm going to convert it to the natural log, base E. So what do I do? Well, I have to start with this natural log. So I have to say ln. And then I use the old argument, which was negative 2z. But then I divide it by the same base, ln, and this time it's of 4. And that would be how I would convert it, okay? One example. Let's look at another example. We can't do too much with that until we know what z is. Then we're going to convert this one, just to look at a couple more examples. We're going to convert the log of 3.4. Base is 3.4. It's a decimal. And it's of the term 7. And we're going to convert it to base 7. Now don't get those confused. One's the argument, one's the base. So we say, okay, we want to go to base 7. So we're going to say we want log base 7 of the number 7. And what did we come from? Well, we'll go back and say the same log. Log base 7 of the old base, 3.4. Okay, now that's how we would type it in if we had a calculator like the TI-84, because it would allow us to enter those different bases. So I'm going to do that with this one because this is a TI-84. And I'm going to go math, alpha math, which gives me the log again. And I say I need 7 to be the base, arrow over, and I want 7 to be the argument. So that's what it looks like. I'm going to arrow over and say that's going to be divided by, and I'll do it again, math, alpha math, and say this is base 7. And the argument here is what the old base was, 3.4. And now I'm going to just come over and say enter and see what it comes out to be. And when I got it, it came out to be 1 point. Let's go to 4 decimal places, 5901. We'll round that to 5901. I'll see that's what it equals. Now, what would happen if I had a TI-83 or an older calculator? Well, an older calculator, I don't have that option of having the different bases. So I'm going to have to use either the common log or I'm going to have to use the natural log. And as we saw on the previous page, it simply doesn't matter which one I use. So this time I'm going to enter it like this. I'm going to use the common log, and I'll say the argument is 7. And I'm going to convert from the old log was the base of 3.4. So I'll say same log, but I'll say the base, the argument will be 3.4, which was the old base, right? So for this one, I'm going to say log of 7 divided by log of 3.4. And when I enter it, you see I get the exact same number. Now, some of you are saying, well, that's a lot easier than what I had to do with my calculator, where I had to go and enter the base because all they had to do was this, and it's your choice. You can do it either way. 1.5901 is our answer both ways.